Hey everybody, Sukanya here. Today we're going to be taking a look at what are direction cosines and what are direction ratios. So direction cosines and direction ratios all revolve around the vector quantities, and that is going to be in the x, y, and z plane. So just putting that forth out there. And we see that on the left we have that plane right over here. And we are going to focus on first identifying what are direction cosines. So in order to understand what direction cosines are, it is first important for you to remember that alpha is always going to be the angle between this vector. So I just drew a random vector OP somewhere in that 3D coordinate plane. And I said alpha is the angle between that vector and the x-axis. Beta is the angle between the vector and the y-axis. And then gamma is the angle between that vector and the z-axis. So just one thing to keep in mind, alpha, beta, and gamma. Now what I'm going to do, I'm going to drop a perpendicular right down there, and I'm just going to label that as, actually, let me label that as M. I'm going to label that as M. So I'm going to find cos of beta, by looking at this triangle right over here. And the reason I'm doing cos is because it says direction cosine, so that's why I'm doing cos. So cos beta is going to be adjacent over hypotenuse. So adjacent is OM. I'm assuming the origin is O. So adjacent is OM. Hypotenuse is this part right over here. That is OP. Now, whenever we're dealing with direction cosines, we know that this is just going to be a constant, right? So I'm actually just going to replace this in for M. So M is going to be equal to cos beta. Okay, similarly, we can do that for cos alpha and cos gamma. And if we do that, the same exact method of dropping a perpendicular and finding cos, we get these equations right over here. And all of these equations are basically direction cosines. One crucial property to note whenever you're solving questions around this is that L squared plus M squared plus N squared is always going to be equal to 1. So whenever they ask you to prove anything, just remember that this is a theorem as well. Another very crucial concept to know about direction cosines is that direction cosines tell you which way a vector is pointing, right? So as I said before, maybe it's 30 degrees from the x-axis, 60 degrees from the y-axis, and I don't know, 40 degrees from the z-axis. These may not be realistic numbers. I'm just giving you an overview. And this basically shows which way it is pointing. It doesn't tell us where the vector starts from, whether it starts from the origin or not. It just tells us the direction where the vector is pointing. While they show you the current direction that a vector is pointing, that magnitude of the vector is going to be equal to 1. In other words, the vector of the direction of cosines magnitude is always going to be equal to 1. So that is another thing to note. Magnitude is always going to be 1. And this essentially means every vector of direction cosines is going to be unique. And that is because the only thing they share is the magnitude, which is 1. Other than that, they are completely different. They have different alpha, they have different beta, and they have different gamma. So every vector of direction cosines is unique. Okay, now for direction ratios. So this is a standard form we are all used to seeing, right? So this is the x component, this is the y component, and this is the z component right over here. So now I am asking you, what are the direction ratios? And this is pretty simple. It's not as difficult as those direction cosines where we have to sort of do cos of something is equal to a constant. No, direction ratios are essentially, in this case, 2, -3, and 5. So basically, it's just those components over there. Now, what if I ask you to find the direction cosines? Well, that involves converting direction ratios to direction cosines. How do we do that? Well, we have this really helpful formula over here, and that says to convert direction ratios to direction cosines, L, and as we discussed before, this L is equal to cos alpha, this M is equal to cos beta, and this N is equal to cos gamma. And alpha is with the x-axis, beta is with the y-axis, and gamma is with the z-axis. You sort of just have to memorize these. And in order to do that, we have L is equal to A over the magnitude. This is the magnitude of the vector. M is equal to B over the magnitude of the vector, and N is equal to C over the magnitude of the vector. So you know what? Let's actually try to find the direction cosines of this vector. So what I'm going to do is that I'm going to find L first. So L is A, and A in this case is going to be the coefficient attached to I. As you guys can see over here, A is the coefficient attached to I. So A is going to be 2 over the magnitude, which is A squared. So 2 squared plus negative 3 squared plus C squared, which is just 5 squared. M is equal to B over square root, or excuse me, B is negative 3, square root of the magnitude, and honestly, I'm just going to simplify this because the denominator is the same for L, M, and N, which is just 38. So I'm going to say 38, and then N is equal to C. C is that 5 over here, so 5 over square root 38. And from there, we have found our direction cosines. You can also find the exact direction that the vector is pointing by setting L equal to cos alpha, so that's square root 38, and then setting M to cos beta, which is negative 3 square root 38, and then N to cos gamma, which is 5 over square root 38, and then taking cos inverse of both sides to find the angle the vector makes with the x-axis, with the y-axis, and with the z-axis. You might have already known, but this vector has a magnitude that is not equal to 1. It's equal to square root 38. So in these cases, the magnitude does not have to be 1. But whenever you have direction cosines, that magnitude has to be equal to 1. So I'm just going to erase this part right over here. And that's actually proves that L squared, M squared, N squared is equal to 1. So we're going to do L squared, which is 4 over 38, plus M squared, which is 9 over 38, plus N squared, which is, 25 over 38. And adding these, we get 38 over 38, which is indeed equal to 1. So that further proves that the magnitude of direction cosines are always going to be equal to 1. And that was a little crash course on direction cosines and direction ratios.